is and how it works. So it is a scanning technique. So you can scan the whole body, but it is mostly used in our field for scanning the brain. And it has an excellent spatial resolution, but a poor temporal resolution. So sometimes I say that it's good instead of excellent. So a quick question on how you think it works. I didn't know for details myself.
I'm glad you don't have points.
That's the point. You can just guess if you don't know. But yes, it is the correct answer. So yeah, before that, scanning techniques usually involved ingesting some substance. But the revolution with the MRI was the fact that you did not have to. So basically, you sit within a. I think I have a picture. Oh, I have a video explaining briefly how it works.
MRI uses protons, which are abundant in the human body. All protons spin, creating a small magnetic charge. When a strong magnetic field is introduced, as is the case in an MRI machine, the protons align with that field. The MRI technician then introduces a radio frequency pulse that disrupts the proton and forces it either into a 90-degree or 180-degree realignment with the static magnetic field. Since the radio frequency pulse pushed the proton against its nature, once this pulse is turned off, the protons realign with that magnetic field, releasing electromagnetic energy along the way. The MRI is able to detect this energy and is able to differentiate various tissues based on how quickly they release energy after the pulse is turned off.
Thank you, NIBIB. So it is a very useful technique. So people have used it for loads of different things. But one day, people have decided to... Oh, no, sorry. I have a last question before. So what about functional MRI? So it's a different type of MRI. What do you think is the difference? All right. Yes, exactly. So you can see differences in neural activity, because when a population of neuron is active, it uses more oxygen, and therefore you can see indirect changes in how oxygen is brought by hemoglobin. So it is an indirect way of visualizing.
Why?
Because so radio signals is
So you said that it's the photon and I need with the magnetic field, so I don't see when the hemoglobin.
So radio signals are a type of magnetic field.
Yeah.
And so at first you align all protons with the magnet, and then you send radio waves on top of that in order to disturb this alignment. And when you stop this radio wave, you will measure the radio signals that will be emitted when they all align back. And with these radio signals, you can distinguish the position, the variety of tissues, etc. That's what I understood from my brief research.
How much link is really there between the hemoglobin that's carried in the blood with the actual activity of the neuron or the brain region?
I know that for a while it was not clearly understood, because it is an indirect relationship. There are probably computational models of that
there are even there are experimental groups working on this, linking blood flow to local. It varies from one area to another.
Yeah.
Because different neuronal types require different levels of energy.
Isn't that the entire premise of fMRI then?
So fMRI it tells you that there is a change in activity of some population somewhere.
It tells you there's a change in the hemoglobin levels, but you decide that there is a change in brain activity.
So hemoglobin in the brain, changes in hemoglobin levels in the brain are usually related to neural activity. But still, this is a possible. Right?
Yeah. We assume they are linked, but there are many problems with this technique. And that's the topic of today's discussion. So, all right. Last question. So, what is a voxel then? Exactly. So you are measuring activity, and the unit that you are measuring is spatial. So it is around 3 cubic millimeters, and it's the fundamental unit of an MRI scan. And you record hundreds of thousands of them.
How many neurons fit in a voxel?
Many, but it depends on the resolution of the scanner. So usually the resolution is measured in the strength of the magnet that is used in the fMRI. And that's why you see sometimes that this fMRI is like 3 Tesla, 7 Tesla. I think the biggest one is 13 Tesla and arrived in Neurospin last year. And they blocked roads because it didn't fit in the regular. So soon it will be, it will extend up to 13 Tesla.
But then what is the resolution?
But it is still not at the level of 1 neuron. It is, I don't know exactly.
So this,
like 1,000 maybe.
For example, bird brain, which is the size of a mouse brain, requires at least 11 Tesla to have a resolution that for an electrophysiologist looks very poor, but you still have probably a few thousand voxels in a mouse or not. So that you convert this into millimeters cube, but it's lower than probably 100 microns by 100 microns. 1 or 200 microns.
And so one day, so researcher wanted to calibrate their fMRI. So they went to the grocery store. They bought a salmon, a dead salmon at the market, and they put it in the MRI. And what happened was surprising. So they even made a poster out of it. So we tried to guess what it's about. So actually, the subject,
it didn't participate. It was forced to participate after.
Exactly. There was no consent. But the subject is 1 meter atlantic salmon and was not alive at the time of scanning. So the task administered to the salmon involved completing an open-ended mentalizing task. So it was shown a series of photographs depicting human individuals in social situations. And the salmon was asked to determine what emotion the individual in the photo must have been experiencing. So they detailed the whole experimental process as usual. And I'll ask you to guess what happened. So what were the results? So these were the type of stimuli that someone was shown. And indeed, they found significant signal change during the photo conditions compared to rest. So then the question is, why? What are we measuring, etc. And so that means that some voxels exhibited an activity that was different between the conditions. And even when you try to control, and like, for example, you ask the analysis to only find clusters of voxels, such that there must be k voxels that are significantly changing and are close together. Even that, they found a cluster of 3 voxels that had a significant change in activity. So, like that, this is the result. So you can clearly see that the brain of the salmon is active during the task.
That's true.
And I'd like to ask you what your conclusion would be. I'll try to guess what was there. Okay. Let's cite it. Bad parameters. So who wrote bad parameters? So what do you mean?
I mean, probably during the processing or the collection of the data, they chose some parameters that sort of triggered this previous findings.
Okay. Like what, for example?
To be honest, I work with this type of MRI, so I'm not pretty familiar with processing because I get focused on pieces, but I know that how you find a significant voxel or what is considered significant is very variable on the step of the processing go. So assuming that in one of the steps could be which specifically is. There's a threshold of this noise ratio or something.
Signal to noise ratio.
It's a very general thing. The idea that if you have a 5% significance threshold, then if you do 100 tests, you will have 5 that are positive, right?
Exactly. Yeah. So we'll significant. So maybe you wrote significant. Okay. Zombie salmon, maybe. So some people disagree that maybe this fish. So this is evidence for consciousness in the dead salmon. I found that somewhere on a SlideShare website. So I don't know what the context was. I hope it was not serious. What?
I didn't know. I don't know if you know the Ig Nobel Award.
Yeah, exactly.
Every year you can have a funny about science.
Yeah, so they wrote. So it's a prize that rewards research that first makes you laugh and then makes you think. And they got it in 2012. Yeah.
Hugo, one question. How many times did they perform the MRI on this dead salmon? Once or twice? Or
I think it's once, but there are many stimuli. But the whole process, they say, lasted 5 minutes.
okay.
So it was not too annoying for him. It was just 5 minutes.
Possibly, yeah. It can't complain anyways.
And so, no, in fact, the arguments was about indeed about controlling for multiple comparisons. So as I said, you are recording hundreds of thousands of voxels, and if you are looking for significant changes between in all of them, you must find something that is significant, even though it is by chance. And so that's what they argue for. So I was hiding the title, but it is argument for proper multiple comparison correction. And this is the Ig Nobel logo. And it had a big impact on research because at the time the poster was presented, 25 to 40% of studies were not using the correct comparisons. And at the time this group won the Ig Nobel, that number had dropped to 10%. But in fact, I found another paper in 2016, so 4 to 5 years later, a team of researchers showing that almost all analysis software used for fMRI research was still using bad correction, and that led to another crisis in fMRI study. And you can again find newspaper titles like all fMRI studies are flawed, etc. So it's like there was this problem, and it must have had very influential, because it's funny, it's a dead salmon, etc. But still, it did not have a big impact as it was reported. So this I found from a paper in 2012, but yet 4 years later there was another.
People have a short memory.
Exactly. So it's really weird. Yes, it's almost a title. So we can have a first discussion time about whether you are using multiple comparisons, if you maybe use fMRI, and if you correct for these multiple comparisons. So I'm not familiar with any other example in which you are.
This happens all the time, even without fMRI. You know, when you present a bar graph that has more than 2 bars, then you should do it. If you compare, have many, I mean, at least for me, I usually do multiple comparison only because I have several conditions. So it's not really right, but if you have 5 conditions, you have to.
The correction are within a space, or what they mean by multiple comparison correction?
So, for example, if you have a t-test, it's good for comparing 2 samples. If you do a t-test to compare 2 samples among them, then your pure t-test is not valid because you're going to run several times the t-test. So you need to add a correction. There are many ways to do correction. Actually, some of them are very conservative, so they reduce the significance a lot. Some of them are less. So I don't know if there is a obvious way, because there are many corrections. Like Bonferroni is the easiest correction.
That's what they mentioned.
But you have to divide, for example, the power of the test by the number of tests. That's the easiest. But it reduces very fast. I mean, if you have 10 different pairs to compare, then your usual 5% becomes 0.5. The level is much harder to reach. So you have some control that are maybe a bit more specific. I'm not sure. I know the Bonferroni is specific.
But if there was, as I said, another paper in 2016, that means there's no consensus on what to use as
which correction to use.
Yeah, and even when people know, apparently they make software in which there is no proper correction. So people are still ignoring.
Surprisingly, because it's something to do with the fact.
Yeah. Surprisingly, and also it leads to poor results. So maybe people are. Yeah, I hope.
Actually, I have a small question. Like, I was trying to understand what multiple comparisons mean, and I'm still not really sure about it. What multiple comparisons mean? What are we comparing?
Okay. Let's say you have 5 groups of animals. Okay.
Okay.
Or no, time period is something that is often the case. Okay, you have a long experiments, you have a baseline, and then post inducing something, you want to compare periods of 1 minute, but you have 10 minutes afterwards, and the signals change in these techniques. And you would like to know, you don't know the time scale at which your signal changes. So you want to know which time point is significantly different from baseline. So you want to compare all the time points after inhibition to your baseline. Okay. So if you do pair t-test for each of them, if you have 100 time points, you will find about 5 of them being significant. There is no effect. That's the idea. So that's the simple case. Now, I think that we often don't obey this, even if we say, because the point is that you can apply different types of analysis and apply your statistical test and only show one of them in your paper. Okay, this is something I want to bring up because we usually don't apply multiple comparison in this case, but it's something that often happens in biology, and that could tend to result that appears significant. But if you apply 20 different types of analysis with the 5% threshold in each, one of your analysis is going to be significant. It's something we should be careful. It's hard to apply that with the blunt theory because these analyses may be so if they are completely independent, we don't have to. But as soon as you have the same data and you apply analysis, different analysis to the same data, we should apply this function. I think in this case, nobody gets it. But that's the problem. In the proper way to do science, you should know exactly what you will test before you do the experiment. But at least in your science, nobody does this. You do a lot of exploration. You try, you see what happens, you try and see what happens. But when we do this, we should be at least aware that when we apply many different types of analysis,
But thank you for detailing because actually it's a perfect transition because after this shallow introduction, I wanted to maybe dive a bit deeper in the use of statistics because statistics are often wait. How can I know? Are you ready? Okay. Because we use statistics as tools and it's like we memorize them by heart, but we rarely have a deeper understanding of it and why we are using statistics such as p-value testing, t-test, etc. And I think that this example is perfect because at first sight, it is an argument for using multiple comparison correction. But in fact, it might point us to a deeper problem in science, which is the use of our use of statistics. So let's do a bit of epistemology. So maybe you know Karl Popper, which is among the most famous epistemologists. And I think this problem might trace back to his view. So another question is, what do you think distinguishes a science from a pseudoscience according to him? Can you join? So yes, in science, we try to formulate hypotheses that are falsifiable. And that means we never prove theories, we can only reject them. And how do we reject them? It is through this use of statistics and statistical tests that involve p-value. And after Karl Popper came Fisher, and so Ronald Fisher, who is a statistician, he had a friend called Muriel Bristol, and she claimed that she was able to tell whether the tea or the milk was added first to a cup. And Ronald Fisher didn't really believe it. So he designed the first experiment using a null hypothesis. And so a null hypothesis is the default hypothesis that you try to reject. And this hypothesis was formulated as he cannot tell the difference. So he designed his experiments. So he thought that if the p-value was lower than a threshold, then the null hypothesis should be rejected. And the threshold is necessarily arbitrary. And according to Fisher, 1/20, so 5%, is a good threshold. But now what is a p-value? So next question. So when you compute the p-value, what are you really doing? So, okay. Yeah, okay. So most of you have answered that when you compute a p-value, you compute the probability of the null hypothesis being incorrect. And I think this is the main mistake that we make, and that that is the cause of many problems in reproducibility and also for dead salmon, is because it is not that you are actually computing the probability of collecting this data or more extreme data, given that your null hypothesis is correct. And in other words, it is the probability of collecting the data by chance. And so it is not actually the same if you look, for example, at the actual equation, the actual formula. Wait, exactly. There's a book about this.
This is why it's called the t-test.
Yes, probably. No, but it's actually how it was introduced, the Fisher's test. So
I don't think everyone got it. Everyone.
And it's perfect for today. And so, okay, what we want to compute usually is the probability of your theory being correct given the data you observe. But what you are actually computing is not that at all. You are actually computing the probability of getting your data given that the null hypothesis, so T bar, is correct. And you are ignoring all other factors. So this is Bayes' formula, and it actually tells you that the probability of a theory being correct given the data, what you want to compute, is this multiplied by some prior information about your theory being correct, and also compared to all other alternative theories. So you are both ignoring that. So the prior knowledge, but also how other alternative theories compare to the null hypothesis. So in my opinion, it is not enough to reject the null hypothesis if competing hypotheses are not more probable. And so and for example, this this typical view of science, so what your grandmother thinks you're doing, we don't actually prove anything. We disprove things because we are basing our methodology on a specific user statistic, which is the p-value p-value testing. But what we actually do is this. We don't actually provide much information about theories being true or false, which is kind of sad as scientists, I think. And of course, people say that Bayesian analysis is better, etc. But I wanted to bring up this debate because I think it's really important to reproducibility, because there's a lot of issues about p-hacking or publication biases, etc. And I think they are mainly based on the use of p-value itself. And so I was interested in hearing.
Thank you, Hugo. That was really nice.